Hello there, and welcome to The Sleep Scientist. Tonight's journey takes us to the very heart of the Earth, to the mountains that breathe fire, to the hidden cracks where molten rock rises, and to the places where the ground itself can come alive in an instant. Volcanoes are not just impressive. They are powerful forces that can shake the planet, cool the entire world, or even build whole new islands overnight. Some eruptions have been heard thousands of miles away. Some send rivers of lava racing faster than a car, or clouds of ash that darken the skies of distant continents. On other planets, volcanoes reach heights taller than Mount Everest or spray ice and water into the vacuum of space. They remind us that planets, whether Earth, Mars, or far beyond, are restless and alive. If you enjoy these gentle journeys, consider liking and subscribing, or share a thought in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, you don't need to do anything at all. Just let yourself settle in. Feel your breathing slow and let your thoughts drift as lightly as ash on the wind. Now let's begin. A single volcano once made the entire planet colder for a year. In 1815, Mount Tambora in Indonesia erupted with such force that it changed the climate of the entire Earth. Ash and sulfur shot high into the stratosphere, where winds carried them around the globe. This cloud blocked enough sunlight to lower temperatures worldwide. Crops failed in Europe, famine spread through Asia, and in North America, the year became known as the year without a summer. Frost struck in June, snow fell in July, and harvests withered in the fields. The eruption was the largest in recorded history, releasing more energy than millions of nuclear bombs. Yet, the mountain itself is not widely known outside geology. It is a reminder that a single volcanic event can ripple through the atmosphere and touch lives far away, long after the fire and ash have faded from view. Krakatoa's eruption was so loud it circled the Earth 4 times. In 1883, the Indonesian volcano Krakatoa exploded with a sound so intense it shattered eardrums 40 miles away. The pressure wave rippled outward, circling the globe not once, but 4 separate times, recorded on barometers across continents. Sailors at sea, thousands of miles distant, reported hearing what they thought was cannon fire. Closer to the island, entire coastlines were reshaped by tsunamis, and tens of thousands of people lost their lives. The sky filled with ash and sunsets turned crimson for years. Artists painted strange, blood-red horizons without realizing they were witnessing the lingering signature of Krakatoa. The eruption was a global event, one that showed the world how a single volcano could reach into every corner of the planet, not only with sound, but with ash, with waves, and with light itself. Pyroclastic flows can race faster than a jet plane taking off. A pyroclastic flow is one of the most dangerous volcanic hazards. It is a searing avalanche of ash, gas, and shattered rock that rushes down the slopes of a volcano. Temperatures inside can exceed 1,000 degrees. The mixture is so heavy, it hugs the ground, and so fast, it can reach speeds of hundreds of miles per hour, faster even than a jet during takeoff. Nothing in its path can survive. It was a pyroclastic flow that buried Pompeii under Mount Vesuvius and another that destroyed the city of Saint-Pierre on Martinique in 1902. Witnesses described the flow as a roaring wall of fire and dust, appearing almost instantly. Scientists study them with drones and models because no one could possibly survive inside one. Pyroclastic flows are the reason so many volcanoes are not just dangerous, they are nearly impossible to escape once they begin. Some lava burns hotter than molten steel. Lava is molten rock, and depending on its chemical makeup, it can vary greatly in temperature. The hottest types, known as basaltic lava, can reach more than 2,100 degrees Celsius, far hotter than steel when it is forged. At these temperatures, the rock glows a brilliant orange or white and can melt almost anything it touches. The air above it shimmers with heat waves, and even at a distance, the radiating warmth is overwhelming. Yet not all lava is so fast and fluid. Some types are cooler, thicker, and creep along in slow, glowing fronts. For scientists, lava offers a chance to watch the planet's interior spill onto the surface. For people nearby, it is both beautiful and terrifying, a glowing reminder that the Earth beneath us is still a furnace burning away in silence until it chooses to rise. Olympus Mons on Mars is a volcano the size of France, is a volcano. On the red planet Mars sits the largest volcano in the solar system. Olympus Mons is nearly 16 miles tall, more than twice the height of Mount Everest, and so wide it could cover the entire country of France. If you were standing on its slopes, they would seem gentle because the mountain stretches outward for hundreds of miles. Its base is bordered by cliffs taller than any on Earth, and its summit holds a crater the size of a small country. Olympus Mons is thought to have erupted for hundreds of millions of years long ago, when Mars was more geologically active. Today it is quiet, perhaps extinct. Yet the sheer scale of it makes Earth's greatest volcano seem tiny. Olympus Mons is proof that planets can build mountains beyond anything we could imagine, monuments of fire and stone that dwarf our world's tallest peaks. One eruption created an ash cloud that grounded plains worldwide. In 2010, Iceland's Eyjafjallajökull volcano erupted in a series of ash-spewing events that would have seemed small in past centuries. But in the modern age, it disrupted something unexpected: air travel. Volcanic ash is made of microscopic shards of glass and rock, sharp enough to sandblast airplane windows and clog jet engines. When Eyjafjallajökull erupted, its ash cloud spread across Europe. Airspace was shut down for days, stranding millions of passengers. Airlines lost billions of dollars, and scientists scrambled to map the drifting particles with satellites. It was a reminder that volcanoes can affect us in new ways, not just with local destruction, but by touching the delicate systems that connect the world. The eruption was modest compared to Tambora or Krakatoa, but its impact on modern society was enormous. Even a small volcano can reach across continents in surprising ways. Mauna Loa is so heavy, it actually bends the Earth's crust. Hawaii's Mauna Loa is the largest volcano on Earth, and when measured from base to summit, it is also the tallest mountain in the world, rising more than 33,000 feet from the seafloor. It is so massive that its weight presses the crust downward, creating a vast depression in the ocean floor. This sag is called isostatic adjustment, and it means that Mauna Loa is not just a mountain sitting on the Earth. It is a mountain reshaping the Earth beneath it. The volcano covers more than half of the big island of Hawaii. It has erupted dozens of times in recorded history, and though it is monitored closely, it remains active. For those who live nearby, Mauna Loa is both a home and a reminder that the ground underfoot is not fixed, but bending under the sheer weight of a mountain made of fire. Stromboli has erupted almost non-stop for 2,000 years. On a small island off the coast of Italy, the volcano called Stromboli has been erupting so regularly that sailors once used it as a natural lighthouse. Every few minutes, fountains of lava spurt into the air, throwing glowing rocks down its slopes. This pattern has continued for thousands of years, earning Stromboli the nickname, the lighthouse of the Mediterranean. The eruptions are relatively small compared to catastrophic blasts like Krakatoa, but their constancy is remarkable. To stand nearby at night is to watch fire leap endlessly from the earth, as though the planet itself is breathing. Stromboli is a rare example of a volcano that has been active for the entirety of recorded human history, a steady reminder of the restless forces below. People live on the island still, accustomed to its glowing breath, knowing that fire has always been part of their horizon. Tambora's eruption caused famine across the northern hemisphere. The 1815 eruption of Mount Tambora in Indonesia was not only the most powerful in recorded history, it also led to one of the most devastating famines. The vast clouds of ash and sulfur reduced global temperatures, shortening growing seasons. Crops failed in Europe, China, and North America. In Switzerland, desperate families boiled grass to survive. In New England, snow fell in June, and frost destroyed harvests again and again. Starvation spread in regions that Tambora's eruption had never touched directly. The eruption killed tens of thousands near the volcano, but millions more suffered from its aftereffects. Writers of the time described eerie sunsets, red skies, and bitter cold summers. Even centuries later, the eruption is remembered not just as an explosion of fire, but as an event that starved a world, proving that volcanoes are not local disasters. They are planetary forces. Entire new islands have risen from the ocean in a single eruption. When magma bursts upward through the seafloor, it sometimes builds entirely new land. In 2013, an eruption near Japan created an island that fused with Nishinoshima, growing larger each year. In 1963, Surtsey erupted off the coast of Iceland, creating an island where scientists could watch life slowly take hold on fresh volcanic rock. These islands are fragile at first, made of ash and soft stone. But over time, they can harden into permanent land. Birds arrive, plants begin to grow, and eventually ecosystems take shape. The birth of an island is a rare chance to watch geology in action, creation instead of destruction. To see land rise where once there was only ocean is to witness one of the Earth's most dramatic transformations. New islands remind us that our planet is not fixed, but always building and remaking itself. Lightning can strike inside volcanic ash clouds like a storm of fire. When a volcano erupts, it throws enormous amounts of ash and rock into the sky. Inside those clouds, particles collide and rub together, building up electrical charge, just like in a thunderstorm. The result is volcanic lightning, bolts that flash through the ash, sometimes hundreds of times a minute. The sky glows with eerie light, illuminating plumes that can rise miles into the atmosphere. Pilots have described the sight as flying past a storm made of fire. Unlike regular lightning, volcanic lightning happens in darkness inside ash, where it cannot always be seen from the ground. Scientists use it as a tool because electrical activity often signals how strong the eruption has become. For those watching, the sight is unforgettable. A storm inside a storm where Earth's fury becomes not only hot and violent, but lit with its own sudden fire. Obsidian blades made from volcanic glass are sharper than scalpels. When lava cools almost instantly, it can form volcanic glass called obsidian. Unlike ordinary rock, it has no crystals inside, just smooth, solid glass. Humans have used it for thousands of years to make tools and weapons. Obsidian blades can be sharper than any metal knife. So sharp that even modern surgeons have tested them for use in delicate operations. Under a microscope, a steel blade looks jagged at the edge. But obsidian's edge is nearly perfect at the molecular level. Ancient cultures prized obsidian, not just for its sharpness, but for its beauty. Jet black, sometimes with hints of rainbow sheen. It forms in volcanic areas like the highlands of Mexico or the slopes of the Andes. A piece of obsidian is more than just stone. It is frozen fire cooled so suddenly that lava turned into glass, waiting to be shaped by human hands. Pumice rock from eruptions can float for months across the sea. Pumice is a type of volcanic rock that forms when gas-rich lava cools so quickly it traps bubbles inside. The result is stone that is so light and porous it can float. After some eruptions, entire rafts of pumice drift across the ocean, stretching for miles. These floating fields have been spotted from satellites, slowly moving with the currents. Eventually, pumice rafts break apart and sink, but not before traveling vast distances. Sometimes they even carry seeds, corals, or tiny animals acting as floating ecosystems. In ancient times, pumice was used as an abrasive, and even today it finds uses in cleaning and construction. To hold a piece feels strange, solid rock, but so light it bobs on water. It is one of the few times when something born of fire can take to the sea, carried along as though it weighed almost nothing at all. Some eruptions under ice can melt glaciers in hours. When a volcano erupts beneath a glacier, the results can be dramatic. Heat from the rising magma melts ice at astonishing speed, releasing torrents of water that burst outward as sudden floods. In Iceland, these events are called jökulhlaups, glacial outburst floods triggered by fire beneath ice. Entire rivers can form in hours, rushing across the land and sweeping away bridges, roads, and farms. Beneath the ice, the lava cools quickly, trapping strange formations of glassy rock. Scientists study these hidden eruptions to understand how volcanoes behave under extreme conditions. For the people who live near them, the danger is real. Fire may be hidden by the ice, but its power is no less destructive. To imagine an eruption that never breaks the surface yet can melt miles of ice above it is to realize how much energy still surges beneath our world. Pompeii was buried alive in less than a single day. In 79 CE, Mount Vesuvius erupted with terrifying force, sending a plume of ash, gas, and rock high into the sky. The Roman city of Pompeii, just a few miles away, was quickly overwhelmed. Roofs collapsed under the weight of ash. Pyroclastic flows surged down the mountain, smothering the city in searing heat. Thousands of people were trapped, many frozen in their final moments. The city was lost for centuries, buried beneath layers of volcanic material. When archaeologists rediscovered Pompeii in the 18th century, they found streets, houses, frescoes, and even loaves of bread still in ovens, all preserved by the ash. Today, Pompeii is a window into Roman life, not only a tragedy, but also a time capsule. The eruption reminds us how suddenly a volcano can change history, destroying in hours what had taken generations to build. The Ring of Fire is home to 3/4 of Earth's volcanoes. Stretching around the Pacific Ocean is a vast horseshoe-shaped zone known as the Ring of Fire. Here, tectonic plates collide, slide, and dive beneath one another, creating chains of volcanoes that line coastlines from South America up through North America, across to Russia, down through Japan, and into Southeast Asia. About 3 out of every 4 of Earth's active volcanoes lie in this ring. Some of the most famous eruptions, Krakatoa, Mount St. Helens, Mount Fuji, all belong to this restless boundary. The Ring of Fire also produces powerful earthquakes because the same plate movements that drive volcanoes also stress the crust. For the millions of people who live along its edge, the Ring of Fire is both home and hazard. A reminder that the Pacific is not just a vast ocean, but a rim of fire circling the planet. There are more volcanoes hidden under the ocean than on land. Though towering volcanoes like Etna and Fuji draw the eye, most of Earth's volcanic activity actually happens out of sight. Beneath the oceans, along mid-ocean ridges, magma constantly rises and cools, building new crust. Thousands of submarine volcanoes dot the seafloor, many still active, some taller than mountains, but never seen. Only in recent decades have submarines and remote sensors revealed the scale of this hidden world. Hydrothermal vents, black smokers, and vast lava plains stretch across the deep ocean. These undersea volcanoes may outnumber land volcanoes many times over. Though invisible to most of us, they are essential to how the Earth works, recycling crust, releasing heat, and shaping the ocean basins. When we imagine volcanoes, we often picture mountains. But in truth, the majority live unseen beneath the waves, shaping the Earth quietly in darkness. Yellowstone is a supervolcano capable of changing life on Earth. Beneath Yellowstone National Park lies a massive volcanic system larger than almost any other on Earth. Its caldera stretches for miles, marked by geysers, hot springs, and boiling mud pots. Scientists call it a supervolcano because, if it erupted at full scale, it could cover much of North America in ash and affect global climate. The last major eruption happened over 600,000 years ago. Smaller lava eruptions and hydrothermal blasts have occurred since, but the system remains alive with magma chambers slowly feeding the heat below. Though unlikely to erupt anytime soon, Yellowstone is watched closely by volcanologists because its power could touch the entire planet. To walk among its steaming pools and geysers is to stand above one of the most restless places on Earth. A place where the crust is thin and the breath of a supervolcano rises constantly to the surface. Animals often sense eruptions long before humans do. Stories from villages near volcanoes tell of dogs barking frantically, birds flying away, and cattle refusing to enter barns hours or even days before an eruption begins. Animals seem to detect subtle changes in the earth, vibrations too small for us to feel, or gases and scents we cannot smell. During eruptions of Mount St. Helens and Mount Etna, scientists recorded unusual animal behavior well before the first explosions. In some cases, snakes have even been seen fleeing slopes in the middle of winter when they would normally remain hidden underground. While technology like seismographs and gas sensors is vital, animals sometimes give the first warning. Their instincts, honed over millennia, may be attuned to the restless movements of magma deep below. For people living near volcanoes, noticing the behavior of animals can sometimes mean the difference between safety and danger. Lava lakes bubble like open windows into Earth's mantle. Most lava cools quickly, sealing itself off from the surface. But in rare cases, a crater remains open and a lake of molten rock churns for years, or even decades. These lava lakes are among the rarest sights on Earth. Only a few exist today at Mount Nyiragongo in Africa, Erta Ale in Ethiopia, and Kilauea in Hawaii. The surface roils with fiery waves, cracking and shifting as glowing orange magma circulates beneath. At night, the glow can be seen for miles, casting an otherworldly light. Scientists study lava lakes to understand the dynamics of magma, convection, and gas release. For visitors, the sight is mesmerizing. The planet's inner heat, exposed in a pool of fire, like a direct connection to the deep mantle. Lava lakes are dangerous, yet profoundly beautiful. Windows into Earth's restless interior, always shifting, always alive. Volcanic ash clouds can circle the planet in less than 2 weeks. When a volcano erupts with enough force, the ash can rise all the way into the stratosphere. At that height, strong winds spread the particles far and fast, carrying them around the globe in a matter of days. After Krakatoa erupted in 1883, the ash circled the Earth in less than 2 weeks, dimming the skies on the other side of the world. Scientists recorded brilliant sunsets in London, New York, and beyond, all painted by ash from a single eruption in Indonesia. These particles can remain suspended for months or even years, affecting climate and blocking sunlight. For people nearby, volcanic ash is hazardous to breathe and heavy enough to collapse roofs. But in the upper atmosphere, it becomes a planetary phenomenon, linking faraway places in a haze born from one sudden release of fire and stone. Stratovolcanoes can erupt with the force of nuclear weapons. Stratovolcanoes are tall, steep-sided volcanoes built from layers of lava and ash. Famous examples include Mount Fuji, Mount Vesuvius, and Mount St. Helens. Their eruptions are explosive, driven by thick magma that traps gas until it bursts outward violently. When Mount St. Helens erupted in 1980, the blast released energy equivalent to 24 megatons of TNT, or about 1,600 times the energy of the atomic bomb dropped on Hiroshima. The eruption destroyed forests, reshaped valleys, and reduced the height of the mountain itself. Unlike gentler shield volcanoes, stratovolcanoes often erupt catastrophically, sending ash miles into the air and pyroclastic flows racing down their slopes. Their beauty can be deceptive, snowy peaks rising peacefully above cities, but inside pressure is constantly building. For communities nearby, they are both symbols and threats. To live in their shadow is to live with the knowledge that they hold forces strong enough to rival humanity's most powerful weapons. Shield volcanoes can grow wider than entire mountain ranges. Unlike the tall, narrow shape of stratovolcanoes, shield volcanoes spread out in wide, gentle slopes. They are built from fluid lava that flows easily, traveling for miles before cooling. Over thousands of years, these eruptions create massive structures. Mauna Loa and Mauna Kea in Hawaii are shield volcanoes so large that they cover nearly half of the Big Island. When measured from their base on the ocean floor, they are taller than Mount Everest. Their size is so vast that it is hard to see from the ground. Only from the air or space do their proportions become clear. Shield volcanoes don't explode violently as often as stratovolcanoes, but their eruptions can last for weeks or months, spreading lava across huge areas. These giants remind us that not all volcanic power comes from sudden blasts. Sometimes it comes from slow, relentless flows that reshape landscapes forever. Cinder cone volcanoes can form in just a single eruption. Cinder cones are the simplest kind of volcano. They form when lava fountains spray into the air, cooling into small fragments of rock called cinders. These fragments fall back around the vent, piling up into a cone-shaped hill. Some cinder cones are only a few hundred feet tall, and they can appear almost overnight. In Mexico, the volcano Paricutin began as a crack in a farmer's cornfield in 1943. Within weeks, it grew into a cone, and over the next 9 years, it erupted enough to bury nearby villages. Cinder cones usually burn out quickly, but while they last, they are dramatic. Their eruptions are short-lived compared to larger volcanoes, yet they show how suddenly the Earth can change. For the farmer who watched his field transform into a volcano, Paricutin was a living reminder that new mountains can rise in a lifetime. Antarctica hides active volcanoes beneath miles of ice. At first glance, Antarctica seems like nothing but ice and snow, but beneath its glaciers lie volcanoes, some still active. Mount Erebus on Ross Island is one of the southernmost active volcanoes on Earth. It has a persistent lava lake that bubbles year-round, even in the frozen darkness of polar winters. Scientists have also found evidence of hidden volcanic activity beneath the West Antarctic ice sheet. Eruptions under the ice could melt huge amounts of water, potentially speeding the flow of glaciers into the sea. Studying these volcanoes is difficult, but they are crucial to understanding Antarctica's stability. The idea that one of the coldest, harshest places on Earth hides fire beneath its surface is striking. It shows that even in the most unlikely regions, the deep heat of the planet still rises, shaping the frozen continent from below. Africa's Rift Valley is splitting the continent apart with fire. The East African Rift Valley is a place where the Earth's crust is slowly tearing open. Here, tectonic plates are drifting apart, and magma is rising to fill the gap. Volcanoes like Mount Kilimanjaro, Mount Kenya, and Nyiragongo are part of this dramatic landscape. In some places, new lakes are forming as the land sinks. And in the distant future, the rift may open into a new ocean. The region is both geologically active and densely populated, making its volcanoes especially significant. Nyiragongo, for example, holds one of the world's largest lava lakes, and its eruptions have sent rivers of fire racing into nearby cities. The Rift Valley is a reminder that continents themselves are not fixed. Africa is literally being pulled apart by fire from below, a process that takes millions of years but can still be felt in eruptions today. Japan has more than 100 active volcanoes. Japan sits directly on the Pacific Ring of Fire, and its islands are dotted with volcanoes, over 100 of them still active. Some, like Mount Fuji, are iconic symbols of the nation. Others erupt frequently, sending ash over towns and farmland. The Japanese Meteorological Agency monitors them closely using seismographs, satellites, and gas sensors. Volcanic eruptions in Japan have shaped history, from ancient disasters to modern evacuations. Despite the risks, volcanic soil in Japan is fertile, and hot springs heated by magma are part of daily life. For centuries, people have lived side by side with volcanoes, building shrines, stories, and traditions around them. In Japan, volcanoes are not distant hazards. They are woven into the landscape and culture. The sheer number of active volcanoes shows how dynamic the region is, resting directly above one of the world's most restless plate boundaries. Mount Fuji is beautiful, but it still has the power to erupt. Mount Fuji rises nearly 12,400 feet above Japan. Its snow-capped cone is one of the most famous peaks in the world. Tourists and pilgrims climb it every year, and it appears in countless paintings and photographs. But beneath its serene shape, it is still an active volcano. Its last eruption was in 1707 when ash fell on Tokyo, then called Edo. Scientists believe Fuji will erupt again, though no one knows when. The volcano is monitored constantly, and emergency plans are in place for the millions who live nearby. For Japan, Fuji is both a cultural treasure and a potential hazard. Its beauty hides its danger, reminding us that volcanoes do not stop being volcanoes just because they have been quiet for centuries. To stand at the base of Fuji is to admire its form, but also to know that it is alive beneath the snow. Italy has 3 volcanoes that are still active today. Italy is home to Vesuvius, Etna, and Stromboli, 3 of the most famous active volcanoes in the world. Vesuvius buried Pompeii nearly 2,000 years ago and still threatens the modern city of Naples. Mount Etna in Sicily is one of the most active volcanoes on Earth, with eruptions recorded for thousands of years. Stromboli, on a small island, has erupted so steadily that it glows like a natural lighthouse. Together, these volcanoes have shaped Italy's history, culture, and landscape. They have destroyed cities, but they also create fertile farmland, vineyards, and new land. Italian scientists monitor them carefully because millions of people live within their reach. The fact that one country holds 3 such powerful volcanoes highlights how active the Mediterranean region is, a place where fire and civilization have lived side by side for millennia. Mount Etna has been erupting for thousands of years. Mount Etna on the island of Sicily is Europe's largest active volcano. It rises more than 10,000 feet above the Mediterranean, and its eruptions have been recorded for over 2,000 years. Some eruptions are explosive, sending fountains of lava and ash into the sky. Others are gentle, with rivers of molten rock slowly flowing down its slopes. Over centuries, Etna has built layers of lava and ash, making it one of the most studied volcanoes in the world. The fertile soil around Etna supports vineyards, orchards, and farms, showing how volcanic land can sustain life as well as threaten it. Etna's activity is so frequent that locals are accustomed to its glow. It is both a danger and a symbol, a mountain that continues to grow, shaping the land and the people who live on its slopes. Sailors once navigated the seas by the glow of Stromboli. For centuries, sailors crossing the Mediterranean used the steady glow of Stromboli as a beacon in the night. The volcano, perched on a small Italian island, erupts so regularly that it has earned the nickname the Lighthouse of the Mediterranean. Eruptions occur every few minutes, sending glowing fountains of lava into the air and scattering sparks down the slopes. At night, these fiery bursts could be seen for miles across the sea. In a world before GPS or electric lighthouses, Stromboli's fiery pulse helped sailors find their way through dark waters. Even today, the volcano remains one of the most active on Earth. Its explosions so consistent, they are studied to understand eruption cycles. Stromboli is a rare volcano that became not just a hazard, but a guide, its flame lighting the paths of countless ships over the centuries. Indonesia has more active volcanoes than any other country. Indonesia sits at the heart of the Pacific Ring of Fire, where tectonic plates grind and collide. This location makes it the most volcanically active country on Earth. With more than 120 active volcanoes, Indonesia has witnessed both devastating eruptions and fertile growth. Krakatoa, Tambora, and Merapi are only a few of its famous peaks. Millions of people live near these mountains, farming land enriched by volcanic soils. Yet, the danger is never far away. Some eruptions have reshaped entire regions, sending tsunamis, ash, and pyroclastic flows across islands. Despite this, life continues on their slopes with traditions, stories, and rituals deeply tied to volcanoes. For Indonesians, volcanoes are part of daily life, both feared and respected. The sheer number concentrated in one nation makes Indonesia a laboratory of volcanic power, a reminder of how much the Earth's surface is still alive and moving. The deadliest eruption in history happened in Martinique. In 1902, Mount Pelée erupted on the Caribbean island of Martinique. The eruption unleashed a pyroclastic flow that swept down into the city of Saint-Pierre, killing nearly 30,000 people in minutes. The heat and speed of the flow were inescapable, destroying buildings and leaving almost no survivors. Saint-Pierre, once called the Paris of the Caribbean, was reduced to ruins in a single morning. Only a handful of people lived through the event, including a prisoner in a stone cell. The disaster shocked the world and became a turning point in volcanology. Scientists realized the need to understand these flows more deeply because ash and lava alone could not explain such destruction. The tragedy of Mount Pelée remains the deadliest volcanic disaster in recorded history. A stark reminder that the greatest dangers from volcanoes are often not the lava itself, but the invisible avalanches of air, heat, and ash. Mount Pelée destroyed an entire city in just minutes. On May 8, 1902, Mount Pelée erupted with terrifying speed. A glowing cloud of gas, ash, and rock, a pyroclastic surge, hurtled down the slopes at more than 300 feet. In less than 2 minutes, the city of Saint-Pierre was gone. The eruption left almost nothing standing, and nearly every inhabitant perished. Survivors described a blinding flash and a roar like thunder, followed by suffocating heat. The devastation was so complete that rescuers at first believed no one had survived. The event showed the world how quickly a volcano could erase a city, leaving behind little but ruins and ash. Mount Pelée still stands today, quiet but not extinct. Its slopes, green again with vegetation. Yet the memory of that day remains a warning that volcanic destruction can strike not in hours, but in the span of a breath. Some volcanic craters are filled with colorful, toxic lakes. When a volcanic crater fills with water, the result can be a lake unlike any other. Minerals from volcanic gases and rock dissolve into the water, creating colors that range from deep turquoise to milky white, even blood red. One famous example is Kawah Ijen in Indonesia, whose crater lake glows an otherworldly blue. But beauty can be deceptive. These lakes are often highly acidic, as corrosive as battery acid. The gases bubbling up through the water can be deadly if inhaled. Visitors sometimes see bright blue flames at night created by burning sulfur. Scientists study these lakes to understand the chemistry of volcanoes, but always with caution. They are reminders that volcanoes can create landscapes of both breathtaking beauty and hidden danger, where a tranquil pool might in fact be one of the most toxic places on Earth. Crater lakes can suddenly release clouds of deadly gas. In rare cases, volcanic crater lakes become dangerous time bombs. Carbon dioxide and other gases can build up in the deep water, trapped by pressure. If the lake is disturbed by an earthquake, landslide, or sudden change in temperature, the gas can erupt upward in a deadly wave. In 1986, Lake Nyos in Cameroon released a massive cloud of carbon dioxide, suffocating more than 1,300 people and thousands of animals in nearby valleys. The lake looked calm, but beneath the surface, it was storing invisible danger. Today, scientists monitor similar lakes and use pipes to slowly release gas, preventing another disaster. Crater lakes remind us that volcanoes are not only dangerous when erupting. Even long after the lava cools, the chemistry of a crater can hold enough hidden power to change the fate of entire communities in a single moment. Lava flows can bury entire towns under rivers of fire. When lava pours from a volcano, it moves downhill, following valleys and roads just like water would. Depending on the type of lava, it can race quickly or crawl slowly. Either way, nothing in its path can stop it. Buildings ignite, forests burn, and towns disappear under glowing rock that eventually hardens into black stone. In 2018, Kilauea in Hawaii erupted, covering more than 700 homes with fresh lava. In other eruptions, whole villages have vanished beneath molten rivers. Lava flows rarely move fast enough to outrun a person, but they are relentless, destroying everything they touch. Even after the eruption ends, the hardened rock remains, reshaping landscapes permanently. For those who return, their homes may lie buried beneath fields of cooled lava, silent reminders of the day fire flowed where streets and gardens once stood. Lahars, volcanic mudflows, can move like wet cement avalanches. Not all volcanic hazards come from fire. When heavy rains mix with ash or when snow and glaciers melt rapidly during an eruption, torrents of mud and debris can surge down valleys. These flows, called lahars, behave like rivers of wet concrete. They can travel at highway speeds carrying boulders, trees, and entire houses in their path. In 1985, a lahar from Colombia's Nevado del Ruiz volcano buried the town of Armero, killing more than 23,000 people. The eruption itself was not especially large, but the mudflow was devastating. Lahars can strike hours after an eruption begins, catching communities off guard. Scientists monitor valleys near volcanoes for signs of lahars because they are among the most destructive secondary effects. A lahar is the Earth's water and fire mixed together, surging downward as a thick, unstoppable flood. Some volcanic explosions are so loud they travel around the globe. The eruption of Krakatoa in 1883 created the loudest sound ever recorded on Earth. It was heard more than 3,000 miles away, and barometers around the globe detected pressure waves circling the planet multiple times. Closer to the volcano, the sound ruptured eardrums and flattened forests. Other large eruptions have also created blasts powerful enough to be heard hundreds of miles away. These explosions happen when trapped gases inside magma escape suddenly, releasing colossal energy in an instant. The sound waves travel not just through air, but around the curvature of the Earth. To imagine a single noise so loud it could be heard on distant continents is staggering. It shows that volcanic eruptions are not just local disasters. They are events powerful enough to shake the entire planet, even in ways we can hear and measure thousands of miles away. Volcanic ash has shut down modern air travel across continents. Volcanic ash is not like the soft ash from a fire. It is made of tiny, sharp particles of glass and rock, blasted into the sky by eruptions. Jet engines cannot handle it. Ash melts inside, coating turbines and causing them to fail. In 2010, Iceland's Eyjafjallajökull erupted, and its ash cloud spread across Europe. Airspace was closed for days, grounding more than 100,000 flights and stranding millions of travelers. The disruption cost billions of dollars, showing that even a relatively small eruption can have enormous modern consequences. Ash clouds are tracked by satellites, and flight paths are diverted whenever eruptions occur. For all our technology, the skies we rely on for travel are still vulnerable to the raw power of volcanoes. A single eruption in the right place can bring the air traffic of an entire continent to a sudden stop. Supervolcanoes can release more ash than all other volcanoes combined. Most eruptions are dramatic but local. affecting towns, regions, or at most continents. Supervolcanoes, however, are in a class of their own. When they erupt, they can eject thousands of cubic miles of ash, more than all smaller volcanoes, combined over centuries. The eruption of Yellowstone around 640,000 years ago blanketed much of North America in ash, leaving deposits many feet thick. These kinds of eruptions are rare, occurring only once every hundreds of thousands of years, but their effects are global. Ash can block sunlight, change rainfall patterns, and disrupt ecosystems worldwide. Though none have erupted in human history, the scars they leave, massive calderas stretching for miles, show the scale of their power. Supervolcanoes remind us that even though most eruptions we see are devastating on a local scale, the Earth still holds the capacity for events far beyond human experience. Volcanic eruptions can even change the course of rivers. When a volcano erupts, the flow of lava and debris can transform entire landscapes. Rivers that have flowed for thousands of years can suddenly be blocked, redirected, or even erased. Lava dams form when molten rock pours into valleys, cooling into solid walls that trap or reroute rivers. In some cases, the blockage creates new lakes, which can later burst in catastrophic floods. Mount St. Helens in 1980 dramatically altered nearby rivers, and similar events have occurred worldwide. For people living downstream, such changes can reshape farmland, destroy fisheries, and alter ecosystems permanently. To see a river's path diverted in a matter of hours is to realize that volcanoes are not just mountains. They are architects of geography, drawing new maps with fire and stone. Water may seem eternal, but even it yields to the sudden force of molten rock. In Iceland, eruptions have reshaped the landscape in hours. Iceland is one of the most volcanically active places on Earth. Sitting atop the mid-Atlantic ridge, it is a country built by fire and ice together. Some eruptions there have altered the landscape in the span of hours. The 2010 Eyjafjallajökull eruption melted glacial ice, sending torrents of water and ash across the land. The 1783 Laki eruption poured lava across huge portions of the island, poisoning the air and leading to famine. Icelanders live with this dual reality. Eruptions can destroy farmland, but they also create fertile soils and striking new terrain. Today, volcanic tourism is part of Iceland's identity, with travelers coming to see craters, lava fields, and steaming vents. For Icelanders, the land itself is alive, never fixed, always reshaping itself under their feet. Eruptions remind them, and us, that geology does not move only in deep time. Sometimes it moves in hours. Volcanoes can erupt beneath the ocean and never be seen. Most volcanic activity happens far beneath the sea along mid-ocean ridges where tectonic plates spread apart. Here, lava pours onto the seafloor constantly, yet almost no one witnesses it. Sometimes enormous eruptions occur without ever breaking the surface. In 2018, one of the largest submarine eruptions ever recorded created a massive underwater lava flow near Mayotte in the Indian Ocean. It went unnoticed until scientists detected unusual seismic signals and discovered new seafloor formations. Underwater eruptions build mountains called seamounts, some of which may eventually rise above the ocean as islands. But many remain hidden, shaping the world silently beneath the waves. These eruptions remind us that what we see on land is only part of Earth's volcanic story. Most of the planet's fire is kept out of sight, working in darkness, raising mountains on the seafloor where human eyes rarely look. Hydrothermal vents at volcanoes support alien-like creatures. Along volcanic ridges deep in the ocean, hydrothermal vents spew hot mineral-rich water into the dark. Temperatures can reach hundreds of degrees, yet life thrives there. Tube worms, giant clams, and shrimp live in total darkness, relying not on sunlight, but on chemical energy from the vent water. Bacteria convert sulfur and other chemicals into food, forming the base of these unique ecosystems. To see them is like looking into another world. creatures that glow faintly with forms unlike anything on land. Discovered only in 1977, hydrothermal vents revealed that life can survive in extreme environments once thought impossible. Some scientists believe similar conditions could exist on icy moons like Europa or Enceladus, where hidden oceans meet volcanic heat. These alien-looking communities remind us that volcanoes are not just destructive. They also create oases of life in the most unlikely corners of the Earth. Some fish live around volcanic vents in the deep sea. In the pitch-black waters of the deep ocean, some species exist nowhere else but around volcanic vents. These fish, shrimp, and other creatures rely on the strange chemistry of hydrothermal systems. The vents release superheated water packed with minerals. Bacteria use these chemicals to produce energy, and fish feed on the chain of life that grows from them. Some species have adapted to withstand crushing pressures and high temperatures, thriving in conditions that would kill most life instantly. They live in worlds of constant heat and chemical flow, where survival depends on staying near the volcanic energy source. Without the vents, they cannot survive. Their existence suggests that life can take root in environments very different from the sunlit surface. Studying them helps scientists imagine how life might persist not only on Earth, but in hidden oceans far beyond our world. Volcanoes may have helped spark the first life on Earth. Billions of years ago, Earth's surface was hostile. Oceans of lava, constant bombardments from space, and a thin, toxic atmosphere. Yet somewhere in that chaos, life began. Many scientists believe volcanoes played a role. Their eruptions released gases that helped build the atmosphere. Their underwater vents provided heat and chemicals, creating a perfect environment for early chemistry to turn into biology. Amino acids, the building blocks of life, may have formed near volcanic settings where heat and minerals catalyzed reactions. Today's hydrothermal vents are still studied as analogs for the past. If volcanoes helped life begin here, they might do the same elsewhere, on icy moons or on distant planets with volcanic activity. The connection between fire and life seems unlikely, yet it may be one of the deepest truths of our origins, that in the heart of fire, life first flickered. Volcanic soils are some of the most fertile on the planet. When lava cools and weathers over time, it breaks down into soil that is rich in minerals. These soils, called andesols, are packed with nutrients like phosphorus, potassium, and iron, which make crops thrive. Regions around volcanoes often support dense populations because the land is so productive. Rice paddies in Indonesia, coffee plantations in Central America, and vineyards in Italy all grow on volcanic soil. Farmers have long recognized this paradox. The same forces that can destroy fields in an instant also create the richest land when the eruptions are over. The fertility of volcanic soils is one reason people continue to live near active volcanoes despite the risks. In many places, human civilization is rooted in volcanic landscapes where fire and life are linked together in a cycle of destruction and renewal. Millions of people live directly on volcanic slopes today. Despite the dangers, volcanoes are home to millions. Cities like Naples, Quito, and Kagoshima sit within reach of active peaks. Why do people live there? Fertile soil, fresh water, geothermal heat, and in modern times, tourism and cultural identity all tie communities to volcanic regions. For some, the risk is simply part of life, balanced by the rewards of the land. Scientists and governments work to prepare evacuation plans and monitor activity, but eruptions can still come with little warning. The choice to live on volcanic slopes illustrates humanity's relationship with the Earth, accepting danger in exchange for beauty and abundance. These communities live closer than anyone to the forces that built the planet. To them, volcanoes are not only hazards, they are home shaping traditions, livelihoods, and stories passed down for generations. Ancient civilizations thrived in volcanic regions. From the Roman Empire around Vesuvius to the Mayan cities in Central America, many ancient civilizations grew in volcanic lands. Fertile soils provided abundant harvests, supporting dense populations and complex societies. Volcanic stone was used for building, and obsidian was prized for tools and trade. At the same time, eruptions sometimes ended civilizations, burying cities or forcing migrations. Myths and legends arose to explain the fiery mountains, often portraying them as gods or spirits. In Mesoamerica, volcanoes were worshipped. In Polynesia, they were personified as deities, like Pele. The dual nature of volcanoes, creation and destruction, was understood even then. Ancient people recognized their gifts, but also feared their wrath. Today, archaeologists study these regions not only for their ruins, but for clues about how humans adapted to life on the edge of fire. Civilizations thrived in the shadow of volcanoes, shaped by their cycles. Pompeii's ruins are still preserved beneath layers of ash. When Mount Vesuvius erupted in 79 CE, the Roman city of Pompeii was buried under thick layers of ash and pumice. The eruption happened so quickly that people had little chance to escape. For centuries, the city remained hidden, forgotten beneath the ground. When it was rediscovered in the 18th century, archaeologists found streets, houses, and even artwork remarkably intact. Food was preserved in ovens, graffiti remained on walls, and casts of people captured their final moments. Pompeii is one of the most extraordinary archaeological sites in the world, offering a direct window into daily life nearly 2,000 years ago. The tragedy preserved history in a way nothing else could. Today, walking through Pompeii is like stepping back in time. A city frozen at the exact moment when fire and ash brought its life to a sudden and permanent halt. Volcanoes can trigger tsunamis when they collapse into the sea. When part of a volcanic island collapses into the ocean, it can displace enormous amounts of water. The result is a tsunami, a wall of waves that can travel across oceans. The 1883 eruption of Krakatoa created tsunamis more than 100 feet tall, devastating coastlines and killing tens of thousands of people. In modern times, similar events have occurred on smaller scales, such as during eruptions in Alaska and Indonesia. Tsunamis caused by volcanoes are especially dangerous because they can happen suddenly without the usual warning signs of earthquakes. Scientists study volcanic islands carefully, watching for cracks or shifts that might signal an impending collapse. These events remind us that volcanic hazards are not limited to fire and ash. When volcanoes meet the sea, the results can ripple outward as waves that reach distant shores, carrying the force of an eruption across entire oceans. Volcanoes can split mountains and form giant calderas. Sometimes the force of an eruption is so great that it empties the magma chamber beneath a volcano. Without support, the ground above collapses inward, leaving behind a vast depression called a caldera. Some calderas stretch for miles, dwarfing ordinary craters. Crater Lake in Oregon, for example, formed when Mount Mazama erupted and collapsed about 7,700 years ago. Today, it holds some of the clearest water in the world, filling a basin created by volcanic destruction. Calderas can also be dangerous, as they often mark the sites of supervolcanoes like Yellowstone. To stand at the edge of a caldera is to see the footprint of a collapsed mountain, an entire summit swallowed by its own eruption. These massive scars remind us that volcanoes do not only build mountains, they can also unmake them, leaving behind vast hollows where peaks once towered. Fumaroles hiss out steam and strange gases year-round. Even when a volcano is not erupting, it often releases steam and gases through vents called fumaroles. These openings in the ground hiss with vapor, sometimes forming colorful mineral deposits around them. The gases include water vapor, carbon dioxide, and sulfur dioxide, which can smell like rotten eggs. In places like Yellowstone, fumaroles are part of the geothermal landscape, signaling that magma still lurks below. Some fumaroles are hot enough to burn, while others bubble gently in quiet valleys. For scientists, fumaroles are valuable windows into the chemistry of volcanoes, revealing what is happening deep underground. For travelers, they are eerie reminders that the ground itself is alive, breathing in steam and strange scents. Even when a volcano seems calm, fumaroles whisper of the heat and pressure still working in the depths, waiting for the moment when it might rise again to the surface. Volcanoes release carbon dioxide, sulfur, and chlorine into the air. Eruptions are not just about lava and ash. They also release huge volumes of gas, each with powerful effects on the environment. Carbon dioxide contributes to greenhouse warming. Sulfur dioxide can form aerosols in the atmosphere that reflect sunlight, cooling the Earth temporarily. Chlorine compounds can damage the ozone layer, which protects us from harmful ultraviolet radiation. During large eruptions, these gases can reach the stratosphere, where they may linger for years. Even smaller eruptions release gases daily, part of the natural cycling of Earth's atmosphere. Scientists monitor gas emissions to predict eruptions because changes in gas output often signal magma rising. For people nearby, volcanic gases can affect air quality and health. To watch a volcano breathe out steam and gas is to see more than just a mountain venting. It is Earth itself exhaling a complex, invisible mixture into the sky. Invisible volcanic gases can silently suffocate life. Not all volcanic dangers are dramatic explosions. Some of the deadliest are silent and invisible. Carbon dioxide and sulfur dioxide are both heavier than air, which means they can flow downhill and settle in valleys. In high enough concentrations, they displace oxygen, suffocating animals and humans. Unlike ash or lava, these gases leave no visible warning. In 1979, at Lake Manone in Cameroon, a sudden release of carbon dioxide from volcanic sources killed dozens of people instantly. Such events show that even when a volcano looks calm, it may still be venting gases in dangerous ways. Scientists place sensors around volcanoes to detect changes in gas concentrations, and communities are warned to stay away from low-lying areas during unrest. These invisible emissions remind us that not all volcanic threats roar with fire. Some arrive silently in the stillness of valleys, taking life without a sound. In some valleys, carbon dioxide pools thick enough to kill animals. Carbon dioxide is colorless, odorless, and heavier than air. In volcanic regions, it can seep out of the ground in invisible flows. Because it sinks, it collects in depressions and valleys. Animals wandering into these zones may collapse without warning. In Cameroon, herders have found cattle lying dead in pastures where carbon dioxide had pooled overnight. In Italy, near Mount Vesuvius, certain caves are known as valleys of death because of similar gas accumulations. For humans, the danger is just as real, though often less visible. Scientists measure these areas carefully because a changing gas output can signal a larger eruption on the way. To see a peaceful valley and know that the air itself may be unbreathable is unsettling. It reminds us that volcanoes shape not only the land and sky, but even the invisible spaces we move through. Volcanic eruptions can inject millions of tons of sulfur into the sky. During major eruptions, sulfur dioxide is released in massive quantities. Once it reaches the stratosphere, it reacts with water to form fine droplets called aerosols. These aerosols spread around the globe, reflecting sunlight and cooling the planet. After Mount Pinatubo erupted in 1991, global temperatures dropped by nearly a full degree Fahrenheit for several years. The skies turned hazy, and sunsets glowed deep red. Sulfur aerosols can also damage the ozone layer, leaving Earth more exposed to ultraviolet radiation. The amount of sulfur a volcano releases depends on its size and magma composition, but the effect can be planetary. Eruptions like Tambora and Pinatubo show that volcanoes can act as climate engines. cooling Earth even as they spew fire. To imagine millions of tons of sulfur drifting above us is to realize how deeply volcanoes connect Earth's surface to its atmosphere. Sulfur from volcanoes can create strange blue flames. In some rare cases, volcanic gases burn with an eerie light. At Indonesia's Kawah Ijen volcano, sulfuric gases seep from cracks in the ground. When ignited by the heat of the volcano, they burn with a brilliant electric blue flame. At night, the sight is otherworldly, rivers of glowing blue fire running down the slopes. These flames are not lava, but burning gas, fueled by sulfur that liquefies and combusts when exposed to oxygen. The effect is so striking that tourists and photographers travel to Kawah Ijen specifically to see it. Workers in the area mined solidified sulfur deposits, carrying heavy loads from the crater, often within sight of the glowing flames. The phenomenon is rare, but it shows that volcanoes can create forms of light and fire that seem almost alien. Blue fire reminds us that volcanic landscapes hold surprises far beyond lava alone. Volcano monitoring now saves thousands of lives every year. In the past, volcanic eruptions often struck without warning, catching communities unprepared. Today, advances in monitoring technology have changed that. Seismographs detect tremors caused by rising magma. Gas sensors measure changes in emissions. Satellites watch for swelling of volcanoes or heat signatures at their summits. Together, these tools give scientists the ability to forecast eruptions days or even weeks in advance. When Mount Pinatubo erupted in 1991, monitoring allowed the evacuation of tens of thousands of people, saving countless lives. Monitoring centers now keep constant watch on dangerous volcanoes, alerting nearby populations to evacuate if necessary. While not every eruption can be predicted perfectly, the progress has been dramatic. Volcano monitoring shows how science can turn knowledge into protection, reducing the human cost of Earth's most powerful natural events. Seismographs can detect magma moving underground. Before many eruptions, volcanoes start to talk. Seismographs pick up tiny earthquakes caused by rock cracking as magma forces its way upward. Scientists look for swarms of quakes clustered beneath the volcano, changes in depth with time, and special signals called harmonic tremor, a steady vibration that can mean fluids are moving. Long-period events triggered by magma and gas sloshing through cracks add another clue. One plot rarely tells the whole story, so volcanologists combine seismic data with ground deformation and gas readings to decide if pressure is truly building. The pattern matters. Hours to days of increasing quake counts, shallowing depths, and tremor can signal that magma is rising toward the surface. Seismographs don't predict the exact moment of an eruption, but they turn silent rock into a readable logbook, giving communities precious time to prepare when a volcano wakes up. Satellites can spot changes in volcanoes from space. From orbit, satellites watch volcanoes constantly. Thermal cameras see heat at vents and fresh lava. Radar interferometry measures tiny changes in ground height, sometimes just centimeters, as magma inflates or deflates chambers below. Multispectral sensors track ash plumes and sulfur dioxide drifting high in the atmosphere. Because satellites revisit the same spot frequently, they can build timelines. A summit swells, gas spikes, heat brightens, then ash appears. This viewpoint is vital for remote or dangerous volcanoes where ground instruments are sparse. When combined with seismic networks, satellite data helps confirm whether unrest is shallow and rising or deep and fading. Even small eruptions can be mapped in near real time, helping aviation reroute around ash. Space-based eyes have turned the world's volcanoes into a global dashboard, quiet most days, but with clear signals when pressure begins to build. Gas sensors can warn of eruptions before they happen. Magma carries dissolved gases, mainly water vapor, carbon dioxide, and sulfur dioxide. As magma ascends, pressure drops, and those gases escape. Instruments on the ground and in the air sample vents and plumes to track how much and what kind of gas is rising. A jump in sulfur dioxide can mean fresh, gas-rich magma has arrived. Shifts in ratios like CO2-SO2 can reveal whether magma is still deep or has moved shallow. Portable sensors, fixed stations, drones, and even satellites all contribute. Because gas can change quickly, frequent measurements are key. A classic warning pattern is a sustained increase in total emissions paired with seismic unrest and swelling of the volcano. No single clue guarantees an eruption, but gas trends often move first, a chemical whisper that pressure is mounting. When combined with other data, those whispers can trigger timely evacuations. Drones now fly into craters too dangerous for people. Some measurements matter most at the source, right over vents and lava lakes. That's where drones come in. Small UAVs can skim hostile craters, collect hot gas with tiny pumps, snap thermal images of fresh lava, and map new fractures with centimeter precision. They go places where helicopters can't safely hover and where humans would face toxic air, rockfall, or sudden explosions. After flights, 3D models help scientists track how domes grow, how vents migrate, and where collapse hazards are forming. During unrest, rapid drone surveys can show if cracks are widening or if temperatures are climbing along new fissures. The result is better, faster situational awareness with far less risk. In modern volcanology, drones are the nimble scouts, bringing home data from the most dangerous edges so people don't have to stand there themselves. Astronauts train on volcanic terrain because it looks like the moon. Volcanic landscapes are natural analogs for other worlds. Apollo astronauts practice geology and navigation on lava fields and cinder cones, learning to identify ash layers, basalt flows, and impact-like features before walking on the moon. The rough, blocky textures of lava flows and pressure ridges mimic lunar basalts. Today's crews still visit volcanic sites in places like Hawaii, Iceland, and Spain's Lanzarote to rehearse sampling, rover operations, and communications delays. Volcanic ash provides realistic dust hazards. Lava tubes offer stand-ins for potential lunar habitats. Practicing in these environments teaches astronauts how to notice subtle changes in rock, color, and structure, collect clean samples fast, and document context under time pressure. In short, volcanoes on Earth help crews learn the field skills they'll need on airless, basalt-covered worlds where every minute outside a habitat counts. Some eruptions have been captured on video from orbit. From the space station and weather satellites, eruptions unfold in sweeping detail. Cameras have recorded towering umbrella clouds blooming in minutes, shock waves rippling outward as perfect circles, and ash columns punching into the stratosphere. Infrared sensors reveal the hottest parts of plumes at night. Lightning detectors map furious electrical storms inside ash. Time-lapse sequences show how winds shear plumes into long filaments that stretch for thousands of kilometers. These views aren't just dramatic, they're practical. Orbital footage helps aviation centers draw no-fly zones around ash, and it helps scientists estimate eruption rates, plume heights, and the amount of gas lofted into the atmosphere. For remote ocean volcanoes, satellite video may be the only record of the event. Space turns a single volcano's outburst into a measurable global signal, visible minute by minute as it evolves. Mars has volcanoes taller than any mountain on Earth. Mars built giants. Olympus Mons rises about 16 miles high and sprawls hundreds of miles across, dwarfing Everest. Nearby the Tharsis Montes, 3 massive shield volcanoes line up along a plateau visible from space. Low Martian gravity and a lack of plate tectonics let eruptions stack in one place for eons, creating mountains with gentle slopes that seem almost flat when you stand on them. Radar and imagery show enormous lava sheets and collapsed calderas, miles wide. Many Martian volcanoes last erupted millions of years ago, but some features hint at relatively recent flows in geologic terms. Studying these behemoths helps scientists understand how planets without moving plates dissipate heat and why Martian volcanism persisted far longer than expected. On Mars, mountain often means volcano, and the scale stretches the imagination. Venus is covered in vast volcanic plains. Thick clouds hide Venus, so radar mapping revealed its surface. Endless volcanic plains, broad shield volcanoes, and pancake-like domes. Basaltic lava appears to have resurfaced huge areas in the planet's past. Geologists see sinuous lava channels thousands of kilometers long and hotspots that resemble Hawaiian shields, but on a continental scale. Recent studies suggest some vents may still be active with subtle thermal changes and new lava flows appearing between radar passes. The planet's crushing pressure and furnace-like heat make fieldwork impossible, so orbiters do the heavy lifting. Venus shows another way a rocky world can work. Without plate tectonics, volcanism may wax and wane in global pulses. Its plains are a reminder that a volcanic planet can mean broad, quiet outpourings that repaint a world, not just explosive mountains punching at the sky. Jupiter's moon Io is the most volcanic place in the solar system. Tidal forces from Jupiter and neighboring moons knead Io like putty, generating intense internal heat. The result is non-stop volcanism, hundreds of active vents, glowing lava lakes, and plumes rising into space. Spacecraft have imaged curtains of lava and fresh flows repainting the surface in sulfur, yellows, reds, and black glass. Some volcanoes erupt so frequently that maps go out of date within months. Io's heat doesn't come from radioactive decay or lingering formation energy. Its tidal heating is writ large, showing how gravity itself can power geology. Watching Io helps scientists understand energy sources that can drive activity on small worlds, and it offers a living laboratory for lava behavior at extreme scales. Compared with Earth, Io is volcanism on fast-forward, brighter, hotter, and always changing. Io's eruptions shoot lava fountains hundreds of miles high. Io's most spectacular displays aren't just lava flows. They're towering plumes, jets of gas, and particles driven by explosive eruptions. Some plumes soar hundreds of miles above the surface, forming umbrella shapes that sunlight catches like ghostly halos. The source is violent. Lava interacts with sulfur-rich materials and trapped gases, releasing energy that blasts material skyward at incredible speeds. Spacecraft have flown through these plumes, measuring their composition and mapping where the fallout snows back onto the moon. On Earth, eruption columns reach the stratosphere. On Io, they reach space. These plumes show how different gravity, temperature, and chemistry can make familiar processes, eruption, gas expansion, fallout, play out on an epic scale. They turned a small moon into a fireworks show of planetary science visible from millions of miles away. Saturn's moon Enceladus sprays water plumes into space. Beneath Enceladus's icy shell lies a hidden ocean warmed by tidal forces. Through cracks near its south pole, the moon vents enormous geysers of water vapor and ice grains into space. NASA's Cassini spacecraft flew through these plumes, tasting salts and organic molecules inside. That discovery transformed Enceladus from an obscure moon into a prime candidate for habitability. The plumes also feed Saturn's faint E-ring, showing how one small moon can shape an entire planetary system. Scientists suspect hydrothermal vents at the ocean floor could provide the chemistry for life. Unlike Earth's volcanoes of fire and rock, Enceladus volcanism is frozen. Yet it may be more promising for biology than many places on our planet. It is a reminder that the most exciting volcanoes may erupt not with molten lava, but with fountains of liquid water in the cold, dark of space. Neptune's moon Triton has volcanoes made of ice. When Voyager 2 passed Neptune in 1989, it revealed something no one expected: black geysers erupting from the icy surface of Triton. These weren't lava plumes, but fountains of nitrogen gas and icy particles, some shooting 5 miles high. Dark streaks on the surface mark where the winds carried them. Triton's frozen crust may be warmed from below, either by a subsurface ocean or by seasonal heating from sunlight. If so, it suggests that volcanism can take many forms: fire on Earth, water on Enceladus, and nitrogen on Triton. The eruptions reshape its alien landscape, covering plains and erasing old craters. Even at the edge of the solar system, more than 2 billion miles away, volcanic processes are alive. The lesson is clear. Volcanism is not just an earthly phenomenon, but a universal way for worlds to breathe out their hidden energy. Scientists call these frozen eruptions cryovolcanoes. On Earth, volcano means lava and ash, but across the solar system, scientists use a broader term: cryovolcano. These cold volcanoes erupt not molten rock, but liquids and gases that freeze quickly in space. On Triton, it is nitrogen. On Enceladus, it is salty water. On Pluto, it may be ammonia slush. The process is the same. Internal heat builds pressure, cracks open, and material vents to the surface. Cryovolcanoes reshape terrain, feed planetary rings, and even alter atmospheres. They expand our definition of volcanism, showing it is not just a fiery force, but a versatile one, sculpting icy worlds as effectively as basalt sculpts Hawaii. Studying cryovolcanoes may also reveal clues about hidden oceans and possibly habitats sealed beneath kilometers of ice. To a geologist, they are as thrilling as Vesuvius or Etna because they prove volcanoes take many surprising forms. Cryovolcanoes spit out water, methane, and ammonia instead of lava. What looks like lava on an icy moon can actually be a slurry of water mixed with exotic chemicals. Ammonia lowers the freezing point, creating antifreeze oceans beneath the surface. Methane can bubble up and vent into thin atmospheres. When these mixtures erupt, they spread across the surface, then quickly harden into icy plains and ridges. On Pluto, NASA's New Horizons mission spotted massive dome-like features that could be ancient cryovolcanoes, some as tall as Mount Everest. Their surfaces appear relatively young, suggesting eruptions happened not billions, but perhaps millions of years ago. That means heat and activity may still linger. While terrestrial lava glows red and molten, cryolava oozes as slush in near absolute zero temperatures, yet both speak the same planetary language. Worlds under pressure will always find ways to let their hidden interiors flow outward. Volcanoes have shaped the atmospheres of planets and moons. Volcanic gases are one of the primary ways atmospheres are born. On early Earth, eruptions released vast amounts of water vapor, carbon dioxide, and nitrogen, laying the foundations for oceans and air. Venus's thick atmosphere, heavy with carbon dioxide and sulfuric acid clouds, may be the legacy of global volcanic outpourings. Even Mars, now cold and thinned, once had volcanoes pumping gases skyward, likely thickening its atmosphere for a time. On moons like Io and Triton, eruptions actively resupply tenuous atmospheres today. Studying these processes helps us understand not just how surfaces evolve, but how climates and skies are built over billions of years. In a sense, to study volcanoes is to study the breath of planets, the way they exhale their innermost chemistry and write their character into the air that surrounds them. Studying volcanoes helps us imagine alien worlds. Volcanoes are a window into how planets release energy. On Earth, eruptions produce basalt plains, mountains, and fertile soils. But when scientists see them on Mars, Venus, or icy moons, they imagine what landscapes they might walk across. Would Martian lava tubes stretch like subway tunnels for miles? Would the cryolava plains of Pluto crunch beneath boots like frozen mud? By comparing volcanic processes across the solar system, researchers can imagine conditions we've never seen firsthand. Volcanism tells us about heat flow, water content, and chemistry, ingredients that shape habitability. In fact, when we design missions to search for life, we often target volcanic terrains because they combine energy, minerals, and sometimes water. Volcanoes are not only natural wonders, they are prototypes of alien environments, helping us guess what lies beyond the reach of today's spacecraft. Planetary volcanoes may hold clues to finding life beyond Earth. Life as we know it needs energy, chemistry, and liquid solvents. Volcanoes, whether fiery or frozen, provide all three. Hydrothermal vents powered by volcanic heat on Earth teem with life independent of sunlight. Similar vents may exist under the ice of Enceladus or Europa, sustained by cryovolcanic cycling. On Mars, ancient volcanic terrains might preserve hot springs where microbes once thrived. Even distant Triton, with its nitrogen plumes, demonstrates that geological activity can refresh surfaces and exchange chemistry with space. For astrobiologists, volcanoes are more than geology. They are beacons of habitability. Each eruption, each vent, is a laboratory that could nurture or reveal life. To search for biology on other worlds, we often begin where volcanism is still at work. Because where there is energy and chemistry flowing outward, the possibility of life is strongest. Earth's volcanic heat may power life deep underground. Far below the sea floor, microbial communities thrive in hot rocks heated by magma. These microbes, called extremophiles, survive on chemical energy rather than sunlight, oxidizing sulfur, iron, or hydrogen. Studies of deep drill cores and hydrothermal vents suggest Earth's subsurface biosphere could outweigh all surface life combined. Volcanic heat creates circulation systems that carry nutrients, water, and energy into these hidden realms. The discovery reshaped biology. Life does not need surface light, only chemistry and warmth. That insight drives the search for extraterrestrial life. If Earth's deep biosphere thrives on volcanic energy, then subsurface oceans of Enceladus, or Mars's ancient hot springs, may once have done the same. In this way, volcanoes don't just shape landscapes. They sustain ecosystems we cannot see, reminding us that the planet is alive at every level, from surface to hidden core. Volcanic eruptions once turned skies blood red at sunset. After massive eruptions, fine ash and sulfur aerosols spread through the upper atmosphere, scattering sunlight. Instead of golden evenings, skies glow crimson, purple, or even eerie green. Historic records describe blood-red sunsets after Krakatoa's 1883 eruption, so vivid that artists painted skies filled with apocalyptic fire. The particles can linger for months or years, tinting skies worldwide. The phenomenon isn't just beautiful. It signals climate disruption as sunlight is reflected back into space and global temperatures dip. For people who witnessed it centuries ago, such colors inspired myths of divine anger or omens of change. Today, scientists measure the scattering with satellites and ground stations to estimate how much material has reached the stratosphere. Volcanic sunsets are both natural wonders and climate markers, a reminder that what happens at a single mountain can paint the entire sky of Earth in otherworldly hues. The sound of Krakatoa's eruption ruptured eardrums 40 miles away. On August 27, 1883, Krakatoa produced one of the loudest sounds in recorded history. The pressure wave ruptured the eardrums of sailors aboard ships 40 miles distant. Barometers around the world registered the shockwave which circled the globe multiple times. The blast was heard clearly 3,000 miles away, as far as Australia and India. People closer by reported walls of sound so powerful they felt them physically in their chests. The eruption destroyed most of the island, generated massive tsunamis, and plunged skies into darkness. Its sound remains a benchmark of natural violence, far louder than jet engines or bombs. In human terms, it was almost incomprehensible. Yet this deafening noise came from a geological process as old as the planet itself. Magma meeting water, pressure exceeding limits, and the Earth releasing energy in an instant heard around the world. Volcanic glass is so sharp it was once used for surgery. When lava cools too quickly for crystals to form, it hardens into volcanic glass called obsidian. This black, glossy stone can be fractured to make edges sharper than steel scalpels. In ancient times, cultures from the Aztecs to the Minoans crafted obsidian blades for ritual and battle. Even today, some surgeons experiment with obsidian scalpels because they can cut cells cleanly without tearing. Under a microscope, the edge of obsidian appears almost molecularly thin, far beyond the refinement of most metals. It's remarkable that a chaotic eruption spewing molten rock can leave behind a material so precise and delicate. From primal rituals to modern medicine, volcanic glass bridges worlds. It is at once a tool of the ancients and a marvel of natural engineering, reminding us that volcanoes create not only destruction, but also materials of extraordinary utility and beauty. Lava tubes can form caves big enough to walk through. When a river of lava flows, the surface can cool and harden while molten rock still rushes beneath. Once the flow drains away, it leaves behind long, hollow tunnels known as lava tubes. These caves can stretch for miles with ceilings high enough to walk beneath, like a cathedral carved by fire. In Hawaii, Iceland, and the Canary Islands, explorers can enter these dark passageways, their walls still rippled with the patterns of flowing rock. Some lava tubes shelter unique ecosystems, home to insects and microbial colonies adapted to the perpetual darkness. On Mars, scientists suspect giant lava tubes may exist, so large that entire cities could fit inside, shielded from radiation. For planetary explorers, these natural tunnels might one day become homes. On Earth and beyond, lava tubes are secret corridors into the volcanic heart of a planet. Entire cities could fit inside collapsed volcanic chambers. After a massive eruption empties a magma chamber beneath a volcano, the surface above may collapse, creating a giant depression called a caldera. Some calderas are vast, tens of miles across, forming craters so large they could easily contain entire cities. Yellowstone's caldera, for example, stretches about 35 miles wide, a landscape of forests, rivers, and geysers sitting atop one of Earth's largest volcanic systems. Crater Lake in Oregon, now filled with deep blue water, is another caldera left behind by collapse. These immense scars are reminders of the scale of eruptions that created them, blasts thousands of times stronger than typical volcanoes. Standing at their edges, it is difficult to imagine the voids that once existed beneath. Calderas show how a single eruption can permanently reshape geography, leaving behind natural amphitheaters big enough to swallow civilization whole. Some volcanic eruptions have created deserts of ash. When volcanoes unleash enormous ash plumes, entire regions can be blanketed in fine gray powder. Unlike fertile volcanic soils that enrich over centuries, fresh ash can smother life, creating barren wastelands. The 2010 eruption of Eyjafjallajökull in Iceland sent ash clouds across Europe, but local farms saw fields buried under layers of grit. After Tambora erupted in 1815, some islands in Indonesia became gray deserts for years. Ash deserts are haunting, flat, dry, and nearly lifeless, like moonscapes on Earth. Over time, rains and winds carve the ash into dunes and ridges, while hardy plants slowly return. Eventually, the same ash enriches the soil, sparking new cycles of fertility, but at first, the transformation is stark. A thriving landscape silenced, its color drained into monochrome gray. Volcanoes can create new life, but in their immediate aftermath, they can also erase it in vast, quiet expanses. Volcanic islands often attract unique species found nowhere else. Isolated volcanic islands are laboratories of evolution. When fresh land rises from the sea, it begins barren. Over time, seeds drift ashore, birds arrive, and insects hitch rides on the wind. With no predators and few competitors, life evolves in unusual directions. The Galapagos Islands, formed by volcanic activity, gave Darwin the insights that led to his theory of evolution. Hawaii, another volcanic chain, is home to plants and birds found nowhere else on Earth. Volcanic soils are rich and fertile, supporting dense jungles and unique ecosystems, yet isolation makes these species fragile. Human arrival often disrupts the balance, and many island species are endangered. Still, volcanic islands remain powerful examples of how geology and biology intertwine. When Earth remakes its surface with fire, life always finds a way to seize the opportunity and adapt into extraordinary new forms. Some eruptions last only hours, others last for decades. Volcanic activity varies wildly in duration. Some eruptions explode with fury in mere hours, exhausting their magma and leaving only silence and ash behind. Others, like Kilauea in Hawaii, can erupt steadily for decades with lava fountains and flows reshaping the landscape year after year. These long eruptions create new land, expand coastlines, and build entire mountains layer by layer. Meanwhile, short-lived eruptions often cause the greatest destruction, catching people unprepared with sudden blasts. Scientists study eruption patterns to understand these differences. Whether a volcano bleeds its energy slowly or releases it in violent bursts, both extremes demonstrate the unpredictable personality of volcanoes. They may whisper for centuries, then roar in a day. Or they may keep up a slow conversation with Earth's surface for generations, leaving behind landscapes both perilous and profoundly beautiful. Lava flows can reach temperatures hotter than a blast furnace. Fresh basaltic lava erupts at temperatures between 800 and 2200 Godric F, hotter than industrial blast furnaces used for smelting metals. Some rare lavas like those rich in komatiite may have erupted at even higher temperatures in Earth's distant past, glowing red, orange, or even white at their hottest. These flows melt everything in their path. Asphalt, steel, and concrete all fail against such heat. Lava doesn't just destroy, it transforms, welding rocks together, igniting forests, and creating new stone landscapes as it cools. For humans, the sight of molten rivers is both mesmerizing and terrifying, a reminder that beneath Earth's crust lies an inferno waiting to surface. Though few can approach safely, thermal cameras and satellites capture the incandescent glow, documenting nature's most intense furnace operating in the open air. Ash particles can stay in the stratosphere for years. Unlike heavier debris that falls quickly, the finest volcanic ash can rise high into the stratosphere where it lingers for years. There it scatters sunlight, creating colorful sunsets, but also cooling the earth below. After the eruption of Mount Pinatubo in 1991, global temperatures dipped by about half a degree Celsius for nearly 2 years, a measurable climate effect from a single event. The ash and sulfur dioxide spread around the planet, forming a thin veil visible even from space. While eventually it settles out, the long residence time in the upper atmosphere makes volcanic eruptions one of the few natural processes that can alter Earth's climate on a global scale almost instantly. It is a sobering reminder that what happens at one mountain can affect the skies, weather, and even agriculture thousands of miles away. The air around a volcano can glow with eerie colors during eruptions. Volcanic gases and ash interact with sunlight in strange ways. At dawn or dusk, the skies near volcanoes can turn vivid shades of purple, red, or even green. At night, eruptions often illuminate their own plumes from within, with incandescent lava casting an otherworldly glow. When volcanic lightning strikes through the clouds, it adds sudden flashes of electric blue. In some cases, gases like sulfur can create faint halos of light around vents, or reflect eerie hues in the atmosphere. Witnesses describe these scenes as apocalyptic or surreal, as though the boundary between earth and sky has been torn. Yet they are natural optics born from scattering, refraction, and the sheer energy released. For those who see it, the glow of a volcano at night is unforgettable, the planet itself appearing alive, painting the air with firelight. Some eruptions have turned day into complete darkness. When enough ash and debris are hurled into the sky, sunlight itself can be blotted out. Accounts from Krakatoa in 1883 and Tambora in 1815 describe entire days plunged into unnatural night. In nearby towns, lanterns were needed at midday, and people stumbled through choking ash under a sky as black as midnight. The psychological effect was as powerful as the physical one, convincing some that the end of the world had come. Such darkness is caused by dense ash particles in the troposphere blocking and absorbing sunlight. The phenomenon is not just local. Global dimming can occur with strange twilight skies seen on distant continents. In moments like these, a volcano asserts its raw influence. A single mountain silencing the sun itself, turning day into night, and reminding us how fragile our ordinary sense of time and light can be. Volcanoes are responsible for some of Earth's most dramatic landscapes. Volcanoes sculpt the planet in ways nothing else can. Towering cones like Mount Fuji rise in perfect symmetry, while jagged calderas collapse into vast craters. Islands like Hawaii and Iceland were born entirely from volcanic fire. Even gentle rolling hills can be the remnants of ancient lava flows worn smooth by time. Volcanic activity also fuels geysers, hot springs, and fumaroles that shape entire regions into surreal, steaming worlds. The diversity is breathtaking. Obsidian fields that glitter black under the sun, pumice plains light enough to float, and cliffs carved from hardened ash. Wherever volcanoes erupt, they leave signatures that last for millennia, a record written into stone. From snowy peaks to steaming jungles, some of Earth's most dramatic and inspiring vistas exist only because fire once rose from the depths to remake the surface in its own image. Volcanic eruptions can melt glaciers and cause catastrophic floods. When volcanoes erupt beneath or near glaciers, the heat can melt millions of tons of ice in mere hours. The sudden deluge of water rushes downhill, creating catastrophic floods known as jökulhlaups. Iceland has experienced many of these where roads, bridges, and entire valleys vanish beneath walls of water mixed with ash and debris. Unlike ordinary floods, these glacial outbursts strike with little warning, powered by both fire and ice. Historical accounts describe rivers rising so fast they swept livestock, farms, and even houses away. The aftermath often leaves a scarred, barren landscape with black ash coating the land and new river channels carved overnight. It's a dramatic reminder that volcanoes interact not just with rock, but also with ice and water. Where glaciers meet magma, nature produces some of its most violent, surprising, and destructive floods, a collision of opposites with devastating force. Not all eruptions explode. Some simply ooze lava for centuries. When people imagine eruptions, they often picture violent explosions, but many volcanoes are far quieter. Shield volcanoes like those in Hawaii erupt gently, releasing slow rivers of basaltic lava that can flow continuously for years, or even decades. These eruptions are not less powerful. They can cover vast areas, adding layer after layer to a volcano's bulk until it becomes one of the largest mountains on Earth. Kilauea erupted almost non-stop from 1983 to 2018, reshaping the Hawaiian landscape, swallowing neighborhoods, and creating new coastline. Instead of sudden blasts, these volcanoes change the world steadily, almost patiently. The lava hardens into new land that is eventually colonized by plants, animals, and people. These slow, glowing outpourings remind us that eruptions come in many forms, not always destructive explosions, but also steady, relentless reshaping that builds as much as it destroys. Volcanoes can reshape coastlines in a matter of days. When lava meets the ocean, it cools instantly, hardening into fresh rock that expands the land. In Hawaii, new black sand beaches appear almost overnight as molten rock explodes into fragments upon hitting the sea. In Iceland, eruptions have created whole new islands where once there was only water. But the sea is not easily claimed. Waves and tides erode the fresh lava, sometimes carrying it away faster than it can accumulate. Still, volcanic eruptions are among the few forces capable of redrawing coastlines so quickly. Entire bays can vanish, peninsulas can appear, and new habitats for life are carved into existence. For humans, it is both inspiring and unsettling. Maps, which usually feel permanent, suddenly need to be redrawn. Where volcanoes and oceans meet, the boundary between land and sea is never fixed. It is alive, always shifting with fire and water. Lava domes grow like slow-motion mountains before collapsing. In some eruptions, thick, sticky lava piles up near a vent instead of flowing away. Slowly, over weeks or months, it builds into a mound called a lava dome. These formations can look almost gentle, swelling like bread rising in an oven, but they are unstable. Gas and pressure continue to build within, and when the dome collapses, it can trigger devastating pyroclastic flows, avalanches of searing ash and gas that rush down at deadly speeds. The dome of Mount St. Helens rebuilt itself multiple times after its famous 1980 eruption, each collapse altering the shape of the mountain again. Domes are deceptive in their calm appearance, hiding immense potential energy within. They embody the tension at the heart of volcanism, the slow patience of geology, combined with the sudden violence of release, building mountains in silence only to unleash chaos in an instant. Volcanic gases can create acid rain miles away. Volcanoes release vast amounts of sulfur dioxide, chlorine, and other gases into the sky. When these gases mix with water in the atmosphere, they fall back to Earth as acid rain. This rain can corrode metals, damage crops, and poison lakes hundreds of miles from the eruption itself. After Mount Pinatubo erupted in 1991, acid rain fell across Southeast Asia, leaving fields yellowed and water supplies tainted. While it eventually dissipates, the short-term effects are striking. Entire forests can be scarred, their leaves burned away by invisible toxins. Acid rain also erodes stone buildings and monuments, leaving a human cost as well as a natural one. Though not as dramatic as lava flows or ash clouds, volcanic gases can ripple silently across continents, showing that eruptions are not just explosions, but also subtle chemical transformations of Earth's air and water. Scientists who study volcanoes are called volcanologists. Volcanologists dedicate their lives to understanding Earth's most fiery phenomena. They climb slopes to measure gas emissions, install seismometers to detect underground rumblings, and map lava flows to reconstruct past eruptions. Their work combines geology, physics, chemistry, and even biology. Since volcanoes affect every layer of the environment, the goal is both scientific and deeply practical, predicting eruptions to save lives. Volcanology is still young as a science, developing only in the last few centuries, yet its insights have transformed disaster preparedness. Every monitoring station, every data set, every analysis helps communities living in the shadow of volcanoes. Volcanologists are translators of the Earth, turning the restless movements of magma into warnings people can understand. Their work is both dangerous and noble, a constant reminder that knowledge, hard-won on volcanic slopes, can mean the difference between catastrophe and survival. Volcanologists often risk their lives to get close to eruptions. Studying volcanoes is not a safe profession. Volcanologists often trek across unstable ground, breathe toxic gases, and work near flowing lava or erupting vents. Some bring instruments right to the crater's edge, knowing that sudden explosions could happen at any moment. Others fly drones through plumes of ash or lower sensors into boiling lakes. Many volcanologists have lost their lives in the pursuit of knowledge, caught by unexpected eruptions or collapses. Yet their courage has saved countless others. By risking themselves, they provide the data that allows evacuations and warnings, preventing tragedies. Their work is a humbling example of human curiosity and sacrifice, standing face to face with Earth's most dangerous power, not for thrill or spectacle, but to understand and to protect. In every eruption studied, there are traces of lives risked and wisdom earned under the shadow of fire. Volcanoes prove that Earth's surface is constantly changing. We often think of continents and mountains as fixed, unchanging features, but volcanoes prove otherwise. With every eruption, new rock is laid down, new islands rise, old landscapes are buried, and coastlines shift. Over millions of years, entire regions can be reshaped, mountain ranges raised, and valleys filled. Even in their quiet periods, volcanoes remind us that magma is moving, pressure is building, and Earth's crust is never truly still. The continents themselves were shaped in part by volcanic activity through deep time. For humans, this change can be unsettling. Homes destroyed, towns erased. Yet, it is also creative. Without volcanoes, there would be no fertile soils, no islands like Hawaii or Iceland, and perhaps no life as we know it. Volcanoes are Earth's way of breathing, and their restless activity is the clearest sign that our planet is alive beneath our feet. Every eruption is a reminder that the planet is still alive. Deep beneath Earth's crust, molten rock churns and circulates, carrying heat from the planet's interior toward the surface. Every time a volcano erupts, it is a visible reminder of this hidden vitality. Earth is not a cold, dead rock drifting through space. It is a living, breathing system with fire at its heart. Each plume of ash, each river of lava, each trembling of the ground is a message from within. The planet is still active, still shaping itself, still evolving. For billions of years, volcanoes have been part of this cycle, renewing the crust, releasing gases, and nurturing new life. To watch an eruption, even from afar, is to glimpse the pulse of the Earth itself. And as frightening as they can be, eruptions are also signs of continuity. They tell us that our world is dynamic, restless, and profoundly alive. And so we come to the end of our journey through 100 fascinating facts about volcanoes. We've wandered from the quiet slopes of shield volcanoes to the explosive force of stratovolcanoes, from glowing lava rivers to the hidden cryovolcanoes of distant moons. Along the way, we've seen how volcanoes can destroy cities in moments, yet also build fertile soils, new islands, and entire landscapes. They are Earth's great paradox, both dangerous and creative, destructive and life-giving. As you drift here at the edge of sleep, think of the deep, steady heartbeat of the planet beneath your feet. The mantle stirring slowly, heat rising, pressure building, and from time to time, the Earth exhaling fire. These eruptions are not just random events. They are part of a rhythm that has been shaping the world for billions of years. Every mountain, every coastline, every valley carries the traces of this hidden force. And it's not just here. Across the solar system, volcanoes glow and sputter in alien skies. Lava fountains leap high above Jupiter's moon Io. Icy plumes burst into space from Saturn's moon Enceladus. And the immense bulk of Olympus Mons on Mars waits silent, the largest volcano known. Volcanism is not only Earth's story. It is a cosmic story, one written into the very process of how worlds are born, change, and live. But tonight, you don't need to hold all of this in your mind. You can let the grandness of it soften into calmness. Imagine yourself resting on a quiet volcanic slope where the lava long ago hardened into black stone. The ground is still warm beneath you, the stars are bright above, and the air is still. The eruption is over. What remains is peace, the calm after fire. Thank you for spending this time with me here on The Sleepy Scientist. If you've enjoyed this journey, consider liking and subscribing or leaving a gentle thought in the comments below. It helps others find their way here too, one sleepy soul at a time. But for now, let the last traces of the day fade away. Let your breathing fall into its natural rhythm, steady and slow. Let the quiet weight of sleep carry you like cooled lava flowing gently downhill. The world will still be here in the morning, reshaped a little, alive as always. Good night.